In this problem, we are going to take a look at how we can use differential equations to help us solve problems involving non-constant forces. So here's the problem. We're going to have a box on a frictionless surface, and it's going to be given a push. And it's going to have, after this push, some initial velocity. But because of air resistance, there's going to be a force that opposes the motion, and it's going to be equal to kV, some constant times its velocity. So basically, as the velocity varies, as this v varies, the force will vary. So if I give this thing a push and the velocity decreases, this force will slowly decrease over time. So it's a non-constant force, which provides a non-constant acceleration. So we can't use the kinematics model to help us solve this problem. The problem being, we want to find the velocity as a function of time, so the v of t equation, which, because it's not the kinematics model, it's not going to look something like this, which we typically have for the velocity as a function of time. It's going to look a little bit different. Actually, it's going to look quite a bit different. So how do we solve a problem that involves a non-constant force? So given, the box is mass m, and so forth. So, solution. So this is a force model type problem because we have some forces acting on this object. So the first thing we're going to do is we're going to draw an FBD. And if we draw an FBD at the box, we're going to have mg pointing down and Fn pointing up. And this force over here, kV, to the left. This v0 is just a velocity vector in the given. It's not a force. It's just its initial velocity. So there's our FBD. The next thing we can do is we can write our force equations. So step 2, we're going to sum the forces. So I'm going to sum the forces in the x direction. And this is going to be minus kV equals MA equals box. And this, sum of the force in the y direction is going to look something like this. There's going to be an Fn minus mg equals MAJ. So that's our template. So in the x direction, we are going to have an acceleration, so that's not 0. In this y direction, it is 0. And because we have a non-constant force, we're going to have a non-constant acceleration. Note here, usually I put a negative sign right there to denote a negative acceleration. But because we're going to dealing with a non-constant force and we're going to start dealing with rates of change of things, I'm not going to put that in, and you'll see why in a minute. So, step 3 is solve. I'm going to need some room here, so I'm going to go up top. So what I need to do here is I need to write a differential equation and solve it. So if you recall, a differential equation is an equation with a variable and one of its derivatives. So here's m, and I can see the right dv dt here for its derivative, because that's acceleration. So what is the goal? The goal is to find an equation of velocity as a function of time. So somehow I see some v's here and I see a t here, but it's a dt. So how do I solve for this to get an equation of v as a function of time? So one technique you can use to solve a variable is called separation of variables, which is basically, in a nutshell, cross multiplying to get all the variables on one side. So I'm going to do this in steps here so we can follow along. So step 1 is to write it. I'll go step 2 here. I'm going to get all the v's on one side and all the t's on one side. Now, This in calculus class you probably looked at as a unit, dv/dt, but we can actually separate these things. It's like a delta v over delta t. So I'm going to cross multiply. So when I do that, I'm going to get minus k. I'm going to bring the m down up top. And I'm going to bring the dt up. And I want to say dv over v. So I've basically cross multiplied. I've disassembled this dv/dt, which you usually have thought as a unit, and I've just cross multiplied it. And that's how we are separating variables, or cross multiplying. So right now I have differentials of t's and v's, which I don't necessarily want. I want v by itself. So how do I undo a derivative? Well, I integrate. So in step 3, I'm going to integrate both sides. I'm going to say integral of k over m dt is equal to integral of dv over v. And both these sides of the equation are relatively simple. You have, this is just a constant, so it's an integral of a dt, and this is a dv over v, which you've probably recognized as a log. So the next step, step 4 I'll call it, is I'm going to integrate. So this becomes minus k over m, and the integral of a dt is a t plus a constant. Call it constant 1. On this side, the integral of a dv over v is an ln of v plus a different constant, constant 2. And in the next step here, I'm going to have two constants. I'm just going to wrap them up into one constant. I'm going to bring this guy over here, just call it constant 3. So constant 1 minus constant 2 is a constant 3, just another constant. So step 5, I'm going to have minus k over m. These are the spring, the coefficient for the wind resistance here in the mass, t plus constant, I'll call it 3, is ln of v. So I'm slowly isolating v is what I'm doing. So now we have ln of v. Well, how do we get v out of an ln? Well, we raise each side to the e power. Raise this whole thing to the e power. Raise this whole thing to the e power. And the ln and e will get rid of themselves. And so the next step I'm going to have, step 6, is v is equal to e to the minus k t over m times e to the c3, which I'm going to now reduce this to another constant. This is a constant to a constant, which I'll just call c4. So this really becomes v equals c4 e to the minus kt over m, which is looking pretty good. Now I have a velocity as a function of time. This is a c4 here. Usually we don't want to just leave constants hanging around. We want to know what value that is. So one other thing that was given in this problem, which I didn't write down, was that at time equals 0, the velocity is v0. So all this is saying is, at time equals 0, v of 0 is v0, which is the initial velocity. So at the instant of time I start looking at this situation, the velocity is v0. So this is called an initial condition. It's very common in differential equations. It helps us find these constants that are floating around. Initial condition. Can't see it quite well. And it basically spells out an initial condition, in this case an initial velocity. So I go back over here and I say, okay, at time equals 0, which basically is e to the 0, at time equals 0, the velocity is v0. So when time is equal to 0, when this t is equal to 0, that's e to the 0. That's the constant. The velocity is v0. So in a nutshell, the constant is the initial velocity. So we can finally write in step 8, I'm breaking this up into really small steps, so there's 8 steps here. So velocity is a function of time is equal to V0 e to the minus kt over m. So what does this look like? Basically what this means is it's an exponential decay type problem. If I look at velocity as a function of time, I start off at time equals 0 at some known velocity here, v0, and as time goes by this thing drops off exponentially towards 0. So you can imagine this, usually our velocity graphs look linear if we have a constant acceleration. Now because of this non-constant acceleration, we have an exponential drop-off of velocity. So there's our final answer. And then once we have this, usually other parts of the question say, what's the acceleration? In which case we would say it's the derivative of the velocity. So we could simply take a derivative of this to get the acceleration as a function of time. Or we might be asked for the position as a function of time, which in case we'd integrate that to get the position versus time. But in this problem, we took a look at a situation where we had a non-constant force acting, a force dependent on its velocity. So we used the force model to draw an FPD, we summed our forces, and we wrote a differential equation simply by using the substitution A is equal to dV dt, and in this particular problem we used the technique of separation of variables. And going back over here to this minus sign issue, so you would think that there'd be a minus sign here because the acceleration's in the negative direction, and if this were a constant acceleration that'd be the case. But because we're dealing with the rate of change here, any changes in velocity, the dV dt, that change, the plus or minus change, delta, is all wrapped up into this dV dt. So basically this accounts for any changes, and therefore we don't write the negative sign here. We let the calculus handle that for us, and if we follow everything through here, we see we get an exponential decay. And that's an example of how to apply the technique of solving differential equations to a non-constant force type problem.